Hello everybody. Today we're going to learn how to make or determine the three-dimensional shape of molecules. In order to do this, we need to determine the Lewis structure first. The two-dimensional shape will give us the three-dimensional shape. A lot of what we're doing is just determining the two-dimensional shape, the Lewis structure, and then we look in a table to determine, based on the two-dimensional structure, we look in the table to determine the three-dimensional shape. So let's get started. I think I'm going to turn off my face here real quick. There we go. Okay, so here's an example. Make sure I have my pen. There we go. So here we have carbon with two sulfurs. Disulfide. Okay, the first step is to determine the two-dimensional shape. So as you recall, what we're going to do is we're going to find the valence, the number of valence electrons that each of these atoms brings to the molecule. So we have carbon and we have sulfur. So let's look at the periodic table. There it is. Carbon is in column 14, sulfur is in column 16. So carbon 14 minus 10 is 4, sulfur 16 minus 10 is 6, but there's two of them. You add that up, 6 times 2 is 12, plus 4 is 16. Okay, the next step is we put the carbon in the center and we're going to predict the shape using single bonds. So I'll put a sulfur there and I'll put a sulfur there. I've used up 4 with those two single bonds. So 16 minus 4, we got 12 left. So let's start stabilizing the outer atoms first. This sulfur has 2 from the single bond. It needs 6 more. 1, 2, 3, 4, 5, 6. This sulfur also needs 6 more. 7, 8, 9, 10, 11, 12. So we just used up all of our valence electrons. There's none left. But notice this carbon still needs 4 more. It's got 2 from each single bond. It wants 8. So what I'm going to do is I'm going to pick a pair of electrons. It doesn't matter which ones you pick. And I'm going to bring them down and they're going to make a double bond. So that carbon now has 4 electrons on that side. I'm going to do the same thing with these 2 electrons. Going to bring it down, make a double bond. So now that carbon, that bond is a double bond, and so carbon gets 4 there. So now carbon has 4 from that double bond and 4 from that double bond, so now it has 8. So let me get rid of okay, so there is the Lewis structure. The next step is to go to the VSEPR table. So to do this, you need to have a copy of the VSEPR table. So here it is. The way you use this table is you start at the far left column. And if you notice on the top, it says places where electrons are found. What that means is where are the electrons found around the central atom. So you start with the central atom. Here, let me fix that. Okay, so this is, you look at the central atom, you count the places where the electrons are found. So if you look at this central atom is the carbon. Well, look, there's electrons found in this double bond on the right and electrons found in this double bond on the left. So that's 2 places where the electrons are found. 2 double bonds. So let's go back to the table. Okay, places with bonding electrons is the next column. Well, there's 2 places with bonding electrons. Places without bonding electrons. Well, none of them were lone pairs. So what this says is that the molecular geometry is linear. And then it gives you an example of what the visual model might look like. So let's go back to the unit packet. The shape drawing will be an S with a carbon with an S, and it's linear, which makes sense because it's only two. Well, it's linear. I was going to say that it's only two atoms, but it's actually three atoms. So well, let's look at this, the next one. We have a chlorine with two oxygens. So that's chlorine dioxide. Okay, so we got chlorine in there, and we've got oxygen. We go to the periodic table. Chlorine is in column 17. 17 minus 10 is 7. 7 electrons. Oxygen is in column 16. That's 6, but there's 2 of them. Okay, 7 plus 12 is 19. Now that's a weird number because it's odd. So how can we have electron pairs and single and double bonds, triple bonds if it's odd? Well, notice that there's a plus sign here. It has a charge. This is a polyatomic ion. So because it's a plus charge, you have to subtract 1 electron to give it that plus charge. So the total is 18 electrons. 18 electrons. I'm going to predict the shape. I'll put the chlorine in the middle because it's the first atom. I'll put an oxygen down here. Oops. Using a single bond, I'll put one down there, and I'll put one up here. I just used up 4 electrons because of the 2 double bonds. I've got 14 left. I'm going to stabilize the outer atoms first, the ligands we call them. There's 6 electrons, 6 on that oxygen. So that's 12 I've used. I've got 2 left. 1, 2. Now notice minus 2 equals 0. Okay, notice that this chlorine, it still only has 6. It needs 2 more. So I need to make a double bond. And it doesn't matter which ones you pick. I'll pick those. I'll bring it down, and I'll make a double bond. And I've got to get rid of the... Okay, I erase that. And there we have it. Okay, there it is. Okay, every atom in that molecule has 8 electrons around it. Now let's look at the central atom, it's chlorine. Notice that there's a single bond, a double bond, and an electron pair. That's 3 places where the electrons hang out, 3 places. So I'm going to go to my VSEPR table, and I'm going to look for the number 3, places where around the central atom where the electrons hang out. So here we have 3s right here. Which one do we choose? Of those 3 places, 2 of them are bonding. We have a single bond and a double bond, and one of them is not bonding. It's an electron pair. So this says that the shape is bent, and this is what it's going to look like right there. So let's go back to our unit packet, and we're going to put the chlorine. There will be a double bond down there with an oxygen, another oxygen down there, and then the 2 electrons on the top. And this is bent. Let's try another one. Okay, SO3, sulfur trioxide. Okay, we have sulfur and we have oxygen. Sulfur is in column 16 and so is oxygen. So that's 6 valence electrons from the sulfur and 6 times 3 from the 3 oxygens. 18 plus 6, that's 24 electrons. So 24 electrons. We've got sulfur in the center. I'll put an oxygen over there, oxygen over here, and an oxygen up there. I've used up 6 electrons to make those 3 single bonds. That's 18. Okay, so now I'm going to stabilize the outer atoms first. 1, 2, 3, 4, 5, 6. That oxygen is good. 1, 2, 3, 4, 5, 6. That oxygen is good. 2, 3, 4, 5, 6. Now that oxygen is good. I've used up 18 electrons, and I have none left. There's none left to stabilize this molecule. So notice that the sulfur, it still only has 6 electrons around it. It needs 2 more. So I'll take those. It doesn't matter, again, it doesn't matter which ones you take, just pick 2. And I'm going to bring that down, and I'll make a double bond right there. So I need to erase these because I just used those 2 electrons in the double bond. Okay, now you're done, because notice that the sulfur has 8 electrons around it. 2 from that single bond, 2 from the top single bond, and then 4 from the double bond. That's 8. Okay, what's the shape of this? Well, let's count the places around the central atom where you find electrons. Well, you have a single bond, and a double bond. 1, 2, 3 places. 3 places. 3 places. Okay, so let's go to our table. Again, you have 3 is around the central atom, so you have 3 choices. Of these choices, all 3 of them are bonding, right? 2 single bonds and a double bond. None of them are lone pairs. So the shape of this molecule is trigonal planar. Let's go back here. I'm going to get rid of those numbers, I think. Okay. So this is trigonal planar. There we go. And the shape of this is like a 3-pointed star. We've got the sulfur in the middle, and we got an oxygen on the top. It's planar, trigonal planar. Oxygen there and an oxygen there. And so the angle between each of these oxygens, the bond angle we call it, is 120 degrees. Right, 120 degrees. Okay. And it's in a plane, it's flat. This is a flat molecule. Okay, let's try SCN. So that this is sulfur cyanide. CN is the cyanide ion that we talked about in class. So sulfur cyanide. We got sulfur in there, we got carbon, and we got nitrogen. Sulfur is 6, right? 6 electrons. Carbon is 4, column 14. Nitrogen, I'm not sure what that is. Okay, so we got to go to the periodic table. There's nitrogen. Nitrogen is in column 15. 15 minus 10 is 5. That's 5. Okay, you add those up, that's 15. Again, that's an odd number, but notice that this has a charge. There's a negative sign on this molecule. It's a polyatomic molecule that has a negative charge. Since it has a negative charge, we have to add 1 electron to it. 16 electrons. Okay, I'm going to put the carbon in the center on this one. I'm pretty sure that that's right. Okay, I just used up 4 electrons. Guessing the shape of this, I used up 4 electrons, so I've got 12 left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so I just used up all of the electrons that I have available, none left over. But notice that this carbon still needs 4 electrons. So again, what you do is you just pick any 2 electron pairs and you're going to bring them down, make a double bond, and then I'll pick these 2 over here and I'll bring it down and make a double bond. Let's get rid of the, oops. Excuse me. Okay. Put that back. Okay, so notice that the central atom here, the carbon, it has 2 places where you find electrons, 2 double bonds. So let's go back to our table. According to this, we got 2 places, no lone pairs, it is linear. This is a linear, there we go, linear. So S, C, N. Okay, let's try one more. Here we have carbon, tetra for 4, chloride. Carbon tetrachloride. Carbon tetrachloride is an interesting substance. Carbon tetrachloride was used widely in industry maybe about 20 years ago because it's a tremendous solvent. It will cut through anything. It was used a lot, for example, in the airline industry because they could take landing gear that get really, really dirty and they just dip it into carbon tetrachloride, count to 10, pull it out, and it's perfectly clean. It's also used in the automotive industry where mechanics, they need to clean a lot of parts that they take out of the car. They just dip it into carbon tetrachloride. It's an excellent solvent for petroleum products like grease and dirty grease. So it was like a magic chemical that would clean things instantly and get into small crevices. Now the problem was the carbon tetrachloride turned out to be cancer causing. So when they found this out, they had to come up with an alternative, and I'm sure they have, but that's the story of carbon tetrachloride. So what's the shape of this molecule? I mean, what is it about the shape of the molecule that determines its properties, which are an excellent solvent? Well, first step, determine the Lewis structure. So we got carbon and we got chlorine. Carbon has 4 and the chlorine has 17 minus 7 minus 10 is 7, but there's 4 of them. So 7 times 4 is 28 plus 4 is 32. 32 electrons. So let's go ahead and guess the shape. We got carbon in the center. Let's put a chlorine there, chlorine down there, chlorine over there, and a chlorine up there. So 32 minus 2468, we got 24 left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. We just used up all our electrons. Okay, but notice we're done because the central atom, the carbon, it has 8 by the 4 single bonds. So that's the shape. So let's go to our table. We've got 4 places and we got 4 choices. Of these places where we find electrons, of the 4 places around the central atom, how many of them are bonding? bonding with other atoms. Well, all four are, and there were no lone pairs. So the shape of this is what we call tetrahedral, and there's an example of the shape. So let's go back to our unit packet. So the shape is tetrahedral, and you might have heard about this in your geometry class. A tetrahedral shape is like a pyramid. So the way I'm going to draw this is I'm going to put carbon in the center. I'll put a chlorine up there, and I'll put a chlorine down there. And then I'm going to draw a wedge. The wedge indicates that that chlorine is coming out of the page, and then I'll draw a dashed line, and that indicates that that chlorine is going behind the page. So this is how artists on a two-dimensional screen, this is how artists indicate that it's a three-dimensional structure. So you just, in your mind, you have to imagine this chlorine coming out of the page, that one going behind it, and these two in the page. And this creates this tetrahedral structure. This tetrahedral structure where this is the bottom of the pyramid on the below, and then this is the top of the pyramid. And notice how each of these chlorines, they form this shape because the bonds, the electrons in the bonds, they're trying to get as far apart as possible. Okay, I'm going to end it here. So I'll see you in the next video. I hope you're doing well. Bye-bye.